Welcome to the second part of the Chinese remainder theorem. Today, let's look at this question over here. We have to calculate 94 exponent 3567 mode 2800. We are going to use the Chinese remainder theorem, the Fermat's theorem, and the Euler's theorem. So let's start. First of all, you have to write 2800 in its prime factorization. So we are going to get 2 exponent 4 times 5 exponent 2 times 7. And this is the same as 16 times 25 times 7. Now, after doing this, whenever you get this type of question, what you have to do is, you have to, now this modulo 2800 has been divided into 3. So we have the 60, mode 16, mode 25, and mode 7. So let's start with the smallest number over here, which is 7. So the first one is, we have to consider for mode 7. You can also start from mode 16, it doesn't matter, or 25. So when you have mode 7, now let's write 94 in terms of mode 7. So you're going to get this. So 94 is congruent to 3 mode 7. Now, because we have an exponent of 3567, we have to bring that. So 94 is the power 3567 is congruent to 3 exponent 3567 mode 7. So in other terms, what we are trying to say is, if you have 94 exponent 3567, it is the same as 3 exponent 3567 in mode 7. Okay, now you have to check for the GCD of 3 and 7, and the GCD is 1. So because the GCD of 3 and 7 is equal to 1, then it means that we can use either Fermat or Euler. So looking at this, because over here we have 7. Because 7 is a prime number, we can straight ahead and use the Fermat theorem. So 3 raised to the power root of 7 will always be congruent to 1 modulo 7. Now, what is root of 7? Remember, with the Fermat's theorem, let me write this. So we are going to use Fermat. Now remember, Fermat said that if you have root of any prime number p, this is the same as p minus 1. So in this case, root of 7 is equal to 7 minus 1, which is equal to 6. So 3 exponent 6 is congruent to 1 mode 7. Okay, so now after getting this is the same as writing 3 raised to the power 6q plus r is congruent to 3 raised to the power r mode 7, where r is the remainder in this case. So our exponent is 3567. So if we divide 3567 by 6, we are going to get 594, and we're going to have a remainder of 3. So in other words, 3 raised to the power 3567 is congruent to 3 raised to the power the remainder, which is 3 mode 7. So you see, what we are trying to do is, in the question gave us a big number, which is 94 exponent 3567, which is also big. So we reduced it to 94 to 3 exponent 3567. Now that is also huge, so we have to reduce it again. So we then got 3 raised to the power 3 mode 7. You see, this is okay to find. So 3 raised to the power 3 is 27, and 27 mode 7 is 6. So our first congruence is 6 mode 7. Okay, so now this is when we consider mode 7. Now let's consider mode 16. So the same procedure, 94 in terms of mode 16. So we're going to get 14 mod 16. Then the exponent will come, so 3, 5, 6, 7 is congruent to 14, 3, 5, 6, 7 mod 16, and the GCD of 14 and 16 is equal to 2. So note over here, because the GCD of 14 and 16 it's not equal to 1, we can't use either Fermat or Euler's theorem. So what do we have to do? We have to check over here. We can use the first exponentation that I used the last time, or simply put 14, we can check 14 raised to the power 4 in mod 16, it's 0. Now, knowing this, we can see that 14 exponent 3, 5, 6, 7 is the same as 14 exponent 4 times 14 exponent 3, 5, 6, 3, and that is indices. Now, upon knowing that 14 exponent 4 is equal to 0, whatever value over here does not matter. So times whatever is over here. So in other words, 14 exponent 3, 5, 6, 7 is equal to 0. So our second congruence is going to be 0 mod 16. Now let's consider the third case. The third case is when we have mod 25. So in mod 25, let's write 94 in terms of that. And we are going to get 19 mod 25. Okay, so 94 exponent 3, 5, 6, 7 is congruent to 19 exponent 3, 5, 6, 7 mod 25. So the GCD of 19 and 25 is equal to 1. So we can use either Fermat or Euler. So over here, you're going to see that 19 rho of 25 should be congruent to 1 mod 25. So using Euler's method. Euler, because over here rho of 25 can be rewritten as rho of 5 squared, where 5 is a prime number. So this is 5 squared minus 5, 1. Remember, we did this the last time, and we are going to get 20. So 19 exponent 20 is congruent to 1 mod 25. In other words, 19 exponent 20 q plus r is congruent to 19 exponent r mod 25. So we need to find the remainder. So having an exponent of 3, 5, 6, 7, if we divide this by 20, we are going to get 178 plus a remainder of 7. So 19 exponent 3, 5, 6, 7 is congruent to 19 exponent 7 mod 25. And 19 exponent 7 mod 25 is 14. So our third congruent will be 14 mod 25. So after using the Euler and Fermat theorem, that is when we go ahead to use the Chinese remainder theorem. So let's write our three congruences. We have 6 mod 7, 0 mod 16, and 14 mod 25. Okay, so first thing, we have to go ahead and check. Over here we can see that GCD of 7 and 16 is equal to the GCD of 7 and 25, which is equal to the GCD of 16 and 25, and this is equal to 1. Now let's find our big M. our big M will always be equal to 2800, because that was what was given in the question. Now let's find big M1. So big M1 is equal to our big M over our small m1. So 2800 over 7. And that is 400. M2, big M2 is equal to big M over small m2, which is 2800 over 16. And that is 175. Our big M3 is equal to big M over small m3, and that is 2800 over 25. And that is equal to 112. Okay, so now let's go ahead and find our N1, N2, and N3. And we know that M1, N1 is always congruent to one mode, small m1. So if m1 is 400, this is going to be congruent to our small m1, which is 7. Okay, so now we have to write 400 in terms of mode 7. And that is always going to be 1. Mode 7. Okay. So if we want our N1 is always equal to 1. Okay. Now let's go ahead and find our M2. M2, N2 is congruent to one mode M2. And our M2 is 175. So 175 and 2 is congruent to 1 modulus small m2, which is 16. So we have to write 175 in terms of mode 16. And that is 15. So now 175 and 2 is congruent to 15 and 2, which is congruent to 1 mode 16. So we can use the Euclidean algorithm to find the inverse of 15 in mode 16. Okay. So if you do that, you're going to see that N2 is equal to 15, because 15 times 15 in mode 16 is going to give you 1. Now let's find M3. M3 and 3 is congruent to one mode small m3. Now M3 is 112, and this is congruent to one mode 25. So we write 112 in terms of mode 25. And that is 12. So 12 mode 25. So the same thing as 112 and 3 is congruent to 12 and 3, which is congruent to one mode 25. So we want the inverse of 12 in mode 25. So the inverse of 12 in mode 25 is 23. So N3 is equal to 23. So after doing this, we now write it in the form of x is equal to, remember, A1, M1, N1 plus. Okay, so let's do that. So we're going to get S is equal to A1. And what is our A1? A1 is 6. What is our M1? 400. And N1, we got 1. So plus A2 is 0. M2 is 175. And N2 is 15. Plus A3. So A3 is 14. N3 is 112 and N3 is 23 plus our big M of T. So our big M was 2800, so 2800 T. Okay, so now if you go ahead and multiply this, let's do that. So 6 by 400 plus 14 times 112 times 23. I'm going to get 38464 plus 2800T. So X is equal to 38464 mod 2800. And this is going to give us 2064. So this is your answer. So if you were to go ahead and to solve this, 94 raised to the power 3567 mod 2800, even using the fast exponentiation, you end up getting this as your answer. Thank you for watching this video. Please, if you like this video, give it a thumbs up, subscribe. See you in the next video.